Hello friends, today we are going to do question from Heat and Thermodynamics. So total we are going to solve 8 questions, and from 1994 we are having 4 questions. From the year 1995 2 questions, and from 1996 also 2 questions. So in totality we are going to solve 8 questions. First question, it was asked in the year 1994, and it states that an ideal gas with a pressure P and volume V and temperature T is expanded isothermally to volume 2V and a final pressure Pi. If the same gas is expanded adiabatically to volume of 2V, the final pressure is Pa. The ratio of the specific heats of the gas is 1.67. The ratio of Pa to Pi is. So in this case, we are given that the same gas is expanded using 2 processes. One is isothermal, and the volume is same for both cases, 2V as well as 2B, and the pressure is called Pi, where I stands for isothermal, and Pa, where A stands for adiabatic, and we have to find out their ratio. So in this case, we are given that we have initial state and this initial state, the pressure is P, volume is V, and temperature is T, and we are given 2 processes. One is our isothermal and second one is our adiabatic. And under both condition, or rather we can both processes, the final volume is said to be 2 times V, and we are also given the specific heat ratio that is our gamma is given as 1.67, which is approximately equal to 5/3. Therefore, from here we can say it is a monoatomic. And in case of isothermal, the final pressure is said to be given as Pi, and for adiabatic the final pressure is given to as Pa, whose ratio we are going to find out. So first of all, let's deal with the isothermal expansion. So we have isothermal expansion, and we can use our ideal, you can say, gas equation, gas law, and which is our PV is equal to nRT. So it means our initial state can be simply represented by this particular equation itself only. So we can say this is our initial state, and we can modify this ideal gas law as per the final state. So we can say our final state, the pressure is called as Pi, volume becomes 2V, and we have our nR, and it is a basically isothermal, so temperature will be same. Okay. So from here we can just solve it for Pi. So we can say our Pi is equal to our Pi is equal to nRT divided by 2V. Okay, and we can just write it as 1 by 2, and we have this as nRT upon V, and nRT upon V we can just write it from here that P is equal to nRT upon V. So this is nothing but initial pressure. Therefore from here we can say our isothermal pressure after the, you can say, expansion is Pi is equal to initial pressure divided by 2. So this is the relationship between the two pressures. Now we come to our adiabatic expansion. Adiabatic expansion. So we can write that our PV raised to power gamma is equal to constant. So once again let us treat this as our initial state, because initially the pressure is P and volume is V, so this is our initial state, and from here we can find out our final state. And final state is our pressure is given as PA and volume is our 2V and raised to power gamma. Okay. And so in this case we can just equate them, and we know that our PV raised to power gamma should be equal to our PA raised to power 2V raised to power gamma. And from here we can see at the adiabatic pressure is equal to our P, and this comes as V upon 2V whole raised to power gamma. V and V cancels out, therefore we get P, and this is 2 raised to power gamma, or we can write this as P 2 raised to power gamma minus 1. So this is a relationship between our gamma we know, so let's substitute it. So we get this as PA is equal to P 2 raised to power minus 5 by 3. So this is relationship between the adiabatic expansion pressure as well as the initial pressure. So we are required to find out the ratio. So we can say our ratio is our PA upon P isothermal, and this comes as our PA is P 2 raised to power minus 1, and this comes as P 2 raised to power minus 5 by 3. Here P and P cancels out, so this comes as our this is minus 5 by 3, and this is minus 1. So we get this as 2 raised power minus 5 by 3, and this will be coming as plus 1, which is equal to 2 raised power, this will be minus 2 upon 3. Okay, and this ratio will be approximately equal to PA upon PI will be approximately equal to 0.63. So this is the ratio of PA upon PI. Next question. It was also asked in the year 1994, and it states that an ideal gas has taken through a cyclic thermodynamic process through 4 steps. The amount of heat involved in these steps are Q1, Q2, Q3 and Q4. Respective values are given to us respectively. The corresponding quantities of work done are also W1, W2, W3 and W4. W1, W2 values are given, but W4 is not given to us. So based on this we have 2 questions. In part A, find the value of W4, and part B, what is the efficiency of the cycle. Okay. So in this case we have to take in account that this is basically a cyclic process. If it is cyclic process, then we can say that the change in internal energy will be equal to 0 over the complete cycle. So we can say for cyclic process, the net change in internal energy, that is our delta U, is equal to 0. Okay. So let's find out part A. And from the first law of thermodynamics, we know that our first law of thermodynamics gives us that our delta U is equal to Q minus W. Delta U is 0, therefore we can say that our Q should be equal to the work done. And for the, you can say, complete cycle, we can just write this as delta U for our cycle will be Q net, W net, and delta U is 0, so we can say Q net is equal to our W net. So this is a minor adjustment we are going to make in the question, and we can find out our Q net. So we can say our Q net will be equal to Q1 plus Q2 plus Q3 and plus Q4. So we substitute the values. We have our 5960, and second one is our Q2 is a minus, so this comes as minus of 5585 minus 2980 plus 3645. So we get our Q net will be equal to our 1040 joules. Similarly, we can find out our W net. W net will be equal to W1 plus W2 plus W3 and W4. And we substitute the values. W1 is our 2200 and this is a minus, so we can say this is a minus of 825 and this is minus of 1100 and plus W4, and this will be equal to over 275 plus W4, and we said that our Q net should be equal to W net, so we can easily replace W net by our Q net, that is 1040. So you can say this is 1040. So from here we get our W4 is equal to 1040 minus 275, and which gives us 765 joules. So this is our W4. And efficiency, that is part B. And part B, we can write our efficiency will be equal to W net upon Q input. Okay. And this Q in is our total heat absorbed. Okay. Q in is our total heat absorbed, because if you see the value of our Q's that are given to us, some value are positive and some values are negative. Okay, so the heat absorbed will be only the positive values of Q. It means 5960 and 3645. So Q in is the total heat absorbed, or we can say positive Q. Therefore, we can write this will be equal to 5960 plus 3645, which will be giving us 9645 joules. And we know our W net is equal to nothing but Q net. So therefore, we can write this as our Q net upon Q in. Thus, we get our efficiency will be equal to Q net is our 1040 and this comes as our 9605. So this efficiency will be equal to close to 10%, 10.82%. Next question. It was also asked in the year 1994, and it states that two bodies A and B have thermal emissivity of 0.81 respectively. One second. Okay. The outer surface area of two bodies are the same. The two bodies radiate energy at the same rate. The wavelength lambda b corresponding to the maximum spectral radiance in the radiation from B is shifted from the wavelength corresponding to the maximum spectral radiancy in the radiation from A by 1 micrometer. If the temperature of A is 580 Kelvin, so we have to find out all these options. Basically, it is that the temperature of B we have to find out, and we have to find out the wavelength, that is our lambda b. Okay. So, one second. Yes, one value is missing here. That is for B it is 0.81, but for A it is 0.01. That was doubtful here. And hopefully rest of data will be correct. Okay, so we have to make this 0.01 and 0.081. Okay, so we are given the emissivity of A and B are given to us. So we can say for body A, so we get emissivity of body A which is our epsilon of A is our 0.01, and we have emissivity of body B, that is epsilon of B is our 0.81, and we are given that they are having same surface areas, outer surface area of same. Therefore we can write that outer surface area of A and B, so it is same. So we can say of area of A is equal to area of B, and let us suppose it is equal to A. Okay. And it is also given that they are radiating energy at the same rate. Therefore we can write that A and B radiate energy at same rate. So we can say our P of A is equal to P of B, and there is a wavelength shift, that the wavelength shift is with respect to our A, and that wavelength shift is of 1 micrometer. So we can say that our wavelength shift, that is for lambda B, wavelength shift, we get our delta B is equal to, not delta but lambda B is equal to lambda A plus 1 micrometer, and temperature of body A is given to us as 5802 Kelvin. Temperature of body A, that is of TA, it is given to us as 5802 Kelvin. So we have to find out our temperature of B, as well as we are going to find out our lambda B. Lambda B is, this is in micrometer. Okay. So here we can use our Wien's displacement law, and this relates with the wavelength of maximum spectral radiance to the temperature. So you can say Wien's displacement law and which says that our lambda max into T is equal to our B, and here B is approximately equal to 2898 micrometer Kelvin. So we can divide this formula into both bodies, body A as well as body B. Therefore we can write for body A, we can say our lambda A is equal to, we have our 2898, temperature is given to us, that is our 5802. So this comes approximately at 0.5 micrometer. And we can say for body B, our lambda B, which we already know is lambda A plus 1 micrometer. So we get this as our 0.5 plus 1. So this gives us lambda B is equal to 1.5 micrometer. So it means option B is correct. Now we can easily find out the temperature based on same law. So we can say temperature of body B will be equal to our 2898 divided by lambda B, which comes as, this is 2898 and divided by 1.5, giving approximately as 1933 Kelvin. So option A is correct because it is 34, closest is this one, so option A and B are correct. A and B are correct. Next question. It was also asked in the year 1994, and it states that a closed container of volume 0.02 meter cube contain a mixture of neon and argon gases at a temperature of 27 degrees centigrade and pressure of 1 into 10⁵ Newton per meter square. The total mass of the mixture is 28 gram. If the molar mass of the neon and argon are 20 and 40 gram per mole respectively, find the masses of individual gases in the container assuming them to be ideal. Universal gas constant is R 8.314 joules per mole Kelvin. And here data is more or less given directly to us, so need not to make a deeper conclusion from there. And so in order to find out, you can say it is given that a mixture consists of, both are ideal gases basically. So we are going to make use of Dalton's law of partial pressure and find out the total pressure. Okay. So we are given that we have ideal gases, therefore we can say that according to Dalton's law of partial pressure, we can say total pressure P will be equal to, because of the neon plus because of the argon. Okay. And individually respectively for each gas, we can just use our, you can say, our ideal gas law, that is PV is equal to nRT. We can say for each gas, ideal gas law and that ideal gas law is our, let's write for first of all neon gas. And for neon gas, we can say that our pressure for the neon multiplied by volume is equal to number of moles for our neon, and this is comes as R multiplied by T. And this we can write a pressure for the neon is equal to number of moles of our neon RT divided by volume. And we can write that our number of moles of neon will be equal to, we have the molar mass of neon, that is M and E, and we are given the molar mass is given, and okay, individual mass we have to find out, molar mass is given, so this comes the individual mass divided by the molar mass. So we get this as our M and E divided by 20. From here we can say that our for neon is equal to, this comes as our M and E upon 20, and this is RT multiplied by divided by V. And same formulation we can make for our argon also. Argon gas, we can say the pressure because of our argon gas will be equal to mass of our argon divided by its molar mass, which is given to us, okay, one second, it is given as gram, so we have to write it as kilogram. So this comes as our 0.02, and this will be also 0.02, and we have this as 40, so this will be giving a 0.04 RT divided by V. So now we can just use our this equation, so we get our pressure P total pressure, that is P will be equal to, because of argon as well as neon, so we can write this as our, because of neon, that by 0.02 RTV plus because of argon RT upon V. And we just sort it out, so we can write P is equal to, we can take RT upon V as common, and this comes as our NE upon 0.02 plus for argon, and this is 0.04, but total mass is given to us as 28 gram, which basically means that M of Ne plus M of our argon is our 0.028 kg. So this is given to us, and we simply substitute the values. We are going to get two equations. One is already given to us, and second equation we are going to form. And pressure is given to us, so we substitute. This will be coming as our 1 into 10 to the power 5. R is our 8.314, temperature is our 300 Kelvin, and volume is our 0.02, and this comes as our neon and plus argon. Therefore, we can say that our mass of neon, and this comes as 50 plus 25 for argon, is equal to 0.8019, and the given equation is our mass of neon plus for argon, we have this as 0.028. So these are nothing but two simultaneous equations. We can just solve this, and solving both the equations, we are going to get that our mass of neon is equal to our 4.076 kg, and mass of argon will be equal to 23.924 gram, and this will be also in grams. I think this was only, yes, individual gases in the container. Next question. It was asked in the year 1995, and it states that a gaseous mixture enclosed in a vessel of volume V consists of 1 gram mole of gas A with gamma, that is Cp by Cv, is 5/3, and another gas B with gamma as 7.5 at certain temperature T. The gram molecular weights of gases A and B are 4 and 32 respectively. Gases A and B do not react with each other and are assumed to be ideal. The gaseous mixture follows the equation PV 19/13 is equal to constant in adiabatic process. So based on this, we have to calculate 4 things. Okay. So part A, it's asked for the number of grams mole of gas B in the gaseous mixture. Basically, number of moles of gas B, and let us suppose those are denoted by N of B. Okay. So we are given 1 mole of gas A. Okay. So we are given that number of mole of gas A is given to us as 1, and its adiabatic ratio, that is gamma of A, is also given to us as 5/3. Its molar mass is given to us, that is M of A is 4 gram per mole, or we can write it directly in the form of kg, that is 0.004. And our NB, let us suppose it is denoted by X, and for the second gas, that our number of moles, that is of NB, is given as X, and gamma B is given to us as 7/5, and its molar mass is given to us as 32, so we can say 0.032 kg, and it follows a adiabatic process. So we can say for adiabatic process, we know that PV raised to power gamma is equal to constant. This is standard law, and it follows that, I think there is, it should be actually PV raised to power gamma, PV raised to power 19 by 13. Okay, so from here we can say that our in this case we have to remember that the mixture is following the adiabatic process. So we can say for adiabatic process of gaseous mixture, so we can write this gamma as gamma effective, and this value of gamma effective is our 19 by 13. Okay. So let's find out for part A. Number of moles, that is our B, and we know that our 1 mole of ideal gas we can write that our C of V is equal to R upon gamma minus 1, and our C of P is equal to gamma multiplied by R, and this is our gamma minus 1. Therefore we can write same formula for both the gases. So we can say for gas A, we can say that our C of V for A will be equal to our R, gamma is given to us, that is our 5 by 3 minus 1, and this comes as our 3 by 2 times R, and we can write our Cp for A will be equal to 5 by 2 times R, and we can write for gas B our C of B will be equal to 5 by 2 times R, and this is C of P for B is equal to 7 by 2 times R, and we are given that, or we can say find out rather, that the total heat capacities for the mixture. You can say that our total heat capacities for the mixture. Okay, and which basically we can write this will be equal to our, we have our two types, so we can just write this as our, for our pressure, that is our total will be equal to our, for molar of A, and this is our Cp of A plus molar for B, and this is our Cp for B, specific for B. Okay, and like we said, NB we are going to take as X, so we can write this as our Na is about 1 and Cp is 5 by 2 upon R, so we can say 1 multiplied by 5 by 2 times R plus this is about X, and this becomes 7R upon 2. And we can just modify it, we can write this as Cp for total will be equal to, we can take R by 2 as common, and this will be coming as our 5 plus 7x. Now similarly we can write for our other specificate, that is based on our volume. So we can say for volume total will be equal to NA CV of A plus NB CV of B, and this will be coming as our R by 2, and we have this as 3 plus 5 of x. Now we are given what is given to us, this. We know that P V raised power gamma effective is constant, or we can say gamma effective is given to us, so we can find out its value. So we can say that our gamma effective, that effective our adiabatic ratio, will be equal to Cp of the total and divided by other part of C of P of total, which will be equal to 5 plus 7x, and this is our R by 2, and we have this as 3 plus 5x, and this is also R by 2. R by 2 cancels out, so this comes as our 5 plus 7x, and this we have 3 plus 5x, which will be equal to 19 by 13, and we have to find out value of x. Now it is quite simple. So we can say this is equal to 19 by 13 is equal to 5 plus 7x 3 plus 5x. So this gives us that the value of x is equal to 2, or we can say the number of moles for B is equal to 2. So this is basically our part 1. Now we come to part B. States that compute the sound of the gaseous mixture at temperature T 300 Kelvin. Speed of the sound basically in the gaseous mixture. So we have a part B, and we know that the speed of a sound in a gaseous mixture, that is our V. So we can write the formula that we are having speed of sound in a gas mixture V will be equal to square root of, and we have this as RT upon M and multiply by gamma effective, M bar rather, and this M bar is nothing but mean molar mass. Okay. So here M bar is our mean molar mass, whose we can calculate, and this mean molar mass, we have two gases, and this can be written as our number of moles of A multiplied with its molar mass plus number for B multiplied with its molar mass, and we have this as summation of both the molar masses, number of moles Na upon Nb. So we simply substitute the values. Na was our 1, so this comes as 1 into 0.0004, Nb we found out is 2.032, and this 1 plus 3. So this comes as approximately will be equal to 0.0227 kg per mole. Now we can just substitute the rest of the values. So we get velocity V, and gamma effective we know is our 19 upon 13 multiply by, and we have our RT. R is our 8.314, temperature is our 300, and we just found out a mean molar mass, that is 0.0227, and this we get velocity will be approximately equal to 401.1 meter per second. And we come to the part C. If T is raised 1 Kelvin from 300 Kelvin, find the percentage change in the speed of the sound in the gaseous mixture. We have raised the temperature and we have to find out the change in the speed. So let us, this is part C, and velocity equation we already know that V is equal to our gamma effective RT upon mean molar mass and its square root. And so only the temperature is changed, that is only T is changed, so this gamma effective R and mean molar mass is going to remain same. Therefore from here we can write our velocity is proportional to square root of temperature T. And this change in velocity, we can say that our delta V upon V will be approximately equal to 1 by 2 delta T upon T. And change in temperature is obviously only 1 Kelvin, therefore this can be written as 1 by 2 multiplied by 1 divided by 300, and approximately this will be equal to 0.00167. And in terms of percentage, we have to find the percentage change, so we can say this will be approximately equal to 0.167%. And we come to part D, states that the mixture is compressed adiabatically to 1/5 of initial volume V. Find the change in adiabatic compressibility in terms of the given quantities. Okay, so we have to find out the compressibility in terms of when it is compressed adiabatically 1/5 of the initial volume V. Part D, we know that our adiabatic compressibility sometimes it is also called as entropic, entropic compressibility for ideal gas that is basically it is denoted by kappa, so the relation is something looks like K, so this is because K of S is equal to -1 upon V, and this gets partial derivative of volume with respect to our pressure and for our S, and this is our 1 upon gamma effective multiplied by P. And for adiabatic process, let us assume that initial pressure is our P of Y, and volume, that is initial volume, is our V of I, which is equal to V. And after adiabatic compression, we can say our final volume which is our Vf is 1/5 of our V volume. And we already know for the mixture is PV raised to power gamma effective will be equal to constant. Therefore, we can write that our P final V final raised to power gamma effective is equal to P initial V initial raised to power gamma effective. So from here we can say our P final is equal to P initial, and we have this as ratio of our volume raised to power gamma effective, and this ratio is over 5. So this comes as P initial is equal to 5 raised to power gamma effective. Therefore, we can say the compressibility, we can divide that into initial as well as final condition. So we can say our initial compressibility, that is our kappa of I, will be equal to 1 upon gamma effective P of I. Similarly, kappa of F is equal to 1 upon gamma effective P of F, and this can be written as, we can just write this as our 1 upon P of S is our P of I, so this becomes our gamma effective P of I multiplied by 1 upon 5 raised to power gamma effective, and gamma effective is given to us as 19 upon 3. So we have our gamma effective is equal to gamma effective is equal to 19 upon 13, and so we can write that our 5 raised to power 19 upon 13 will be approximately equal to 10.51. Okay, so you can say that our let me solve this equation first of all. I can write that my gamma effective will be equal to, this comes as my one second, yeah, so this comes my kappa of I. So I can write this will be equal to my kappa of I, and 5 raised to power minus gamma effective, and from here I can say the change in compressibility will be equal to our final minus initial, which gives us initial, and I have here 5 raised to power minus gamma effective minus 1. Therefore, one second, it becomes complicated. change in the adiabatic compressibility in terms of I think change is, yeah, this is change in compressibility. And okay, we can just put it like this. So we can say our kf upon ki will be equal to our 1 upon 10.51, which is approximately equal to 0.0951. Yes, so we can say that compressibility decreases to approximately 9.5% of its initial value. Or from here we can also say that a reduction of because this is 9.5%, so a reduction of 90.5%. Okay, this becomes, yeah, this total is 9.5, there 5 at 10, yeah, total is 100%. So there is a reduction of close to 90% approximately. Okay. Next question. It was asked in the year 1995, and it states that for the following statements concerning ideal gas at any given temperature T, select the correct options. So statement 1 is the coefficient of volume expansion at constant pressure is same for all ideal gases. So it is talking about coefficient of volume expansion, that is our beta. So let us check for statement A. And the statement A talks about the beta. So we know that coefficient of volume expansion beta is equal to 1 upon V, and this we have for partial derivative of volume with respect to temperature for the pressure P, and for ideal gas PV is equal to nRT. For ideal gas we know that PV is equal to nRT, and from here we can say that our volume is equal to nRT upon P, and for constant pressure we can just derivate it, partial derivate, and you can say for constant pressure we get this partial derivative of volume with respect to the temperature T will be equal to nR upon P. Therefore, we can write that our beta will be equal to 1 upon V, and we have this as nR upon P. And volume we can write in terms of our nRT. So this comes as 1 upon nRT upon P multiplied by nR upon P. And here this nr goes away, and P also cancels out. So this comes as equal to 1 upon T. So it depends upon only, you can say beta is only dependent upon temperature, inversely dependent upon temperature, and it is independent of everything. Okay. So it means option A is correct. A is correct. Now we come to the option B, and it says the average transitional kinetic energy per molecule of oxygen is 3 kT. Well, in this case we can just use a standard law, and that states by basically 3 by 2 kT. Okay, this relationship is by, I think it is called as the Boltzmann law, if I'm not wrong. This comes as 3 by 2 times kT. So it is not dependent upon kT, 3 kT, but it is 3 by 2. So this option is incorrect. And for mean free path, we can just calculate it. So we have our statement C, and according to basic formula for kinetic theory of the gases, we know that our lambda, which is our mean free path, is given as 1 upon square root of 2, and this is pi d square multiplied by n. Here d is the diameter of the molecule, d is the molecular diameter, and n is the number density, that is molecules per unit volume. N is number density. It is also called as a molecules per unit volume. Per unit volume. And for ideal gas, we can write that our PV is equal to nRT. And okay, in this case, let us write this with capital N. So in order to differentiate with small n, and this small n now we can write as our capital N divided by V. So we can write this will be equal to our PV, N will be equal to PV and RT divided by multiply by 1 by V. So here V and V cancels out, so we get this small n is equal to P upon RT. And therefore we can write that our lambda is equal to 1 upon square root of 2 by d square, and this comes as P upon RT. And it is given that, okay, so for constant, we can say for constant temperature, for constant temperature, that is T, we can write that our lambda is inversely proportional to our pressure P. So if our pressure decreases, the mean path is going to increase, okay, and vice versa. Okay, so it means option C is correct. Correct. Okay. And we come to the option D, and option D is same based on this formula, that our average time, you can say translational kinetic energy is given as 3K by 2. So it says that the gaseous mixture, the average translational kinetic energy of the molecules of each component is different. Okay, and we can say this kinetic energy is our 3 by 2 K times T. Here K is our Boltzmann constant. Okay. And so it is, you can say it is determined by only temperature, because it is only temperature dependent, and it is independent of our molecular mass, which we denote as capital M, or it is also dependent on density. So it is independent of these both things. So therefore this statement is incorrect, okay, because it is only determined by the temperature. So we have only option A and C are correct. Next question. It was asked in the year 1996, and it states that at 27 degrees centigrade, 2 moles of ideal monoatomic gas occupy a volume V. The gas expands adiabatically to a volume 2V. Calculate final temperature of the gas, change in its internal energy, and the work done by the gas during this process. So here we are given as initial temperature. So our initial temperature is T1, which is given at 27 degrees centigrade, or we can say 300 Kelvin, and we have 2 moles, so N is equal to over 2, and we have our initial volume V1 is our V, and we are also given the final volume, that is our V2 is given as twice of V, and it is basically a monoatomic gas, and there is a adiabatic expansion. Okay, so we are given that we have monoatomic gas. Therefore we can write that our specific heat of constant volume, that C of V, will be equal to 3 by 2 times R, and we have a adiabatic index, that is our gamma, which is our ratio of C of P and C of V, will be equal to 5 by 3. So we have to find out first of all final temperature of gas. Process is adiabatic, so it is, we can just write the formula directly. So we can say that our for adiabatic process, we can write our temperature volume raised to power gamma minus 1 is equal to constant, or we can say that T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1, which gives us that our T2 is equal to T1 V1 upon V2 gamma minus 1. And we are already knowing that V2 is twice of V and gamma is also, T1 is also known. Therefore, T1 is given to us 300 Kelvin. Therefore, we can write that our T2 is our 300 multiplied by V1 is V and V2 is twice V. Gamma is 5 by 3 minus 1. And this gives us that approximately T2 will be equal to 189 Kelvin. Now we find out the change in internal energy. And we can write the change in internal energy that is our delta of U is equal to our U2 final minus initial. And the standard formula we already know that our U is equal to N C of V multiplied by T. So we substitute it here. Okay. So we can write our delta of U will be equal to, number of moles will be same in both cases, so this becomes N of C of V T2 minus N of C of V of T1. So we can take N of C of V as common, so this becomes as T2 minus T1. Substitute the value. N is our 2, C of P is our 3 by 2 times R, and T2 we know is our 189 minus 300. This comes as our, let's put value of R also, 8.314. So this comes close to as minus 2769 joules. Okay. And we come to our work done by the gas. So it is adiabatic process. So adiabatic process, we know that value of Q is equal to 0. So we know for adiabatic gas, Q is equal to 0. And first law of thermodynamics gives us delta U is equal to Q minus W, which gives us delta of U is equal to minus of W, or we can say that our W is equal to negative of delta of U, that is minus of minus 2769, which comes as 2769 joules. This is the work done by the gas. Next question. It was also asked in the year 1996, and it states that the temperature of 100 gram of water is to be raised from 24 degrees centigrade to 90 degrees centigrade by adding steam to it. Calculate the mass of the steam required for this purpose. So we are given that mass of water is given to us, and we have to find out the mass of steam so that the temperature of the water can be raised from 24 degrees centigrade to 90 degrees centigrade. Okay. So in this case, the data is very important because there are tricky things in this. So we are given mass of water, that that is m of w is our 100 gram, or we can say 0.1 kg, and we are given initial temperature of the water, that is 24 degrees centigrade. Initial temperature of water is temperature of water, and initial it is our 24 degrees centigrade, and the water is to be raised up till 90 degrees centigrade by adding the steam. It means the final temperature of the mixture, which will be consisting of both water as well as the steam which will be added, and that mixture will be of 90 degree centigrade. So we can say that final temperature of the mixture let us call this as TF will be equal to 90 degree centigrade. And okay, and here because it is steam, so we know that the steam's initial temperature will be 100 degree centigrade. So we can say that our initial temperature of steam let us call this as TS. Steam initial temperature is 100 degree centigrade. And first of all, let's try to find out what will be the heat required by the water without the phase change. Okay. So we can say heat required by the water without phase change. Because the temperature of the water is only changing from 24 to 90 degrees centigrade. So there will be no phase change of the water. And we can say that our this Q of W will be equal to our mass of W, specific heat of the W, and our final temperature and initial temperature of the water, that is TWI. We substitute them, we get this as our mass of water 100 gram. Okay, and our C of W is our 4.18, and this comes as 90 minus 24. So we get this as Q of W is approximately equal to 275 joules. Okay. Now as we are going to add steam to the water, the temperature of steam is 100 degrees centigrade and the temperature of the mixture is 90. So obviously some heat will be released by the steam. So you can say the heat released by the steam. Heat released by steam. And during this process it is going to have, or we can say this heat releasing process will be based on two independent processes. First will be the condensation and then will be the cooling process. Okay. So we can say that our the steam at 100 degrees centigrade undergoes two processes, and first process is of condensation and condensation is at 100 degrees centigrade to liquid water at 100 degrees centigrade, and during this process releasing the latent heat of vaporization. And then we are going to have second process that we call as cooling. Cooling of condensed water from 100 degrees centigrade to 90 degrees centigrade. So it means there will be two types of heat that will be released. First will be our latent heat of vaporization, and second will be because of the during this cooling process. So we can say that our heat released during condensation, which is, let us suppose, of Q condensation, Q and D will be equal to mass of steam and latent heat of vaporization. And mass of steam we are going to find out, so this will be MFS. Latent heat of vaporization we know is our 2260. And second, we are going to find out the heat released during cooling. That is our Q cool will be equal to mass of steam, latent, this is our specific heat of water, change in temperature 100 minus 90, and we get from here Q cool is equal to mass of steam we supposed to find out, and this for water is 4.18 multiplied by difference. So this comes as mass of water multiplied by 41.8. So it means the total heat released by steam, that is our QS. QS will be equal to Q condensation plus Q for the cooling, and MS term is common for both, so we can write about Q of steam, mass of steam we can take as common, so this will be coming as 2260 plus 41.8 approximately. We can write this will be our MFS and 2301.8. Now we can use just if there is no loss of energy, so energy will be conserved. So we can write that heat released by the steam should be equal to heat absorbed by the water. Heat released by steam should be equal to heat absorbed by water. So we can say our Qs is equal to Qw, which gives us Ms into 262301.8 is equal to 27588, and this we can say our Ms is equal to 27588, and this is 2301.8, approximately equal to, we have 11.986 grams. So these were total of 8 questions, 4 from 94, 2 from 95 and 2 from 1996. So this completes total 8 questions. Thank you.